welcome to Sunday's edition of Cracking the Cryptic, where today we're going to be looking at a puzzle with one of the most extraordinary ratings we've ever seen on Logic Masters Germany. This puzzle has had, well, it's got a 100% approval rating and 5 stars out of 5 for difficulty, but it has maintained that through, I think, about 50 solves, which is incredibly rare because it only takes one of those 50 people to say this is only 99% to bring the average down slightly. So it's called Bowser's Castle, which is an amusing reference, I guess, to Super Mario, and I've got no idea why. I am notoriously bad at spotting pictures in grids, but there is nothing about this that reminds me of Bowser's Castle, and it's by Emmettcito, or Emmettcito. I'm never sure what the correct pronunciation of Emmettcito's name is, but I do know that their puzzles are normally absolutely incredible. So well, I'm sure we're going to be in for a treat if I can solve this. This is meant to be a bit of a brutal one. It's been recommended to us by the Discord server, who say that it is a fascinating problem. So I'll read you the rules in just a moment, although the rules are very simple today. What to mention before that? Well, if you enjoyed our Bubba Is You stream on Thursday night, tune in on Tuesday night, where we're going to be repeating it. So 10 o'clock Tuesday night is the next time we plan to stream Bubba Is You. If you're one of the 400,000 people who have subscribed to Cracking the Cryptic over these last 4 years, thank you so much for being one of them. And I can tell you that Mark and I spent a very enjoyable hour this morning answering questions that we've received from the community. So that video, which is what we promised once we got to 400,000 subscribers, I hope will go live tomorrow morning UK time. I don't have much editing to do. I've just got to add the sort of intro music and outro music, and we should be good to go. So hopefully I'll get time to do that later on today, and that will be viewable. Anything else to mention? Well, just do have a go at this extraordinary puzzle pack that we've released on Patreon as October's reward. It's called Padlocked, and it's a series of about 15 or 16 lockout lines puzzles. Lockout lines being this new Sudoku rule that's basically creating a craze over on Discord and elsewhere. And the puzzle pack's being put together by some of the great and the good for the world Sudoku constructing community, and it really is a fabulous set of puzzles, and it's not that easy. Some of the puzzles in it are approachable, but judging by the number of correct entries we've received, it's pretty difficult too. So actually, who did we receive an entry from? I will read out the name, because I think it was Carl Cloden is the latest entry we've received. Well done, Carl. You were indeed correct. And you joined Shui and Yan, who solved it yesterday. Now, all that said and done, let's get on with Bowser's Castle. I'll read you the rules. We have got normal Sudoku rules apply. Digits along an arrow, sum to the digit in that arrow's circle, and that's all we've got. So that means those 3 digits there, whatever these were, let's put some numbers in. Let's make them 1, 4, and can't repeat the 4. 1, 4, and 3. 1 plus 4 plus 3 is 8, so we will put 8 in the circle. That's how arrows work. Do have a go. The way to play is to click the link under the video. Now I get to play. Let's get cracking. And it feels like quite a long time since I've done an actual, just a normal arrow Sudoku. I can see that, well, we've got some 3-cell arrows in the grid. Oh, actually, we've got another one there, and another one here. Can't see any others, but all of these, look, can't contain a repeated digit on the arrow, because obviously you can't repeat a digit in those 3 digits, or you'll break the rules of Sudoku. So in each of these cases, the minimum we could put on the arrows would be a 1, a 2, and a 3. 1 and 2 and 3 add to 6. So that means each of these circles here, they aren't unfortunately aligning, or not. Well, actually, maybe they are. There's a sort of box of them here. So maybe what we've got to do is is there some reason these can't be the same digit? Is this a 6, 7, 8, 9 quadruple for some reason? Let me just think about this for a second. Is there some reason why this digit and this digit can't be the same? Not sure. I'm already wondering whether this is something to do with a set puzzle, though. There seems to be a lot going on in row 1 and row 9. There's also an absolute plethora of short stubby arrows in this puzzle. So look. Yeah, so these digits have to be the same. That's a little bit interesting, actually. If you see these digits have to be the same, we can then ask where the purple digit goes in box 7. It's going to have to be in one of those 3 squares, and it can't be here, because if this is purple, that would be purple, and that would repeat purple in box 4. So purple has to be down there. Look, let me just take a quick look at this and see if we can see anything with the... Yeah, similarly with that one, these two have to be up there for exactly the same reason. This cannot be the same digit, otherwise it will reflect here and will repeat in box 4 again. So there's a sort of symmetry going on between this stubby arrow and this stubby arrow. And maybe the same over here, is it? Yes, it is. Ah, okay. The challenge is going to be what that means. Do I have to shade all of these in? The thing I'm struggling with is to see what that actually does. I'm going to end up with a very colourful grid. Let's just take a quick look at it. I think we get left with something like this. These are also short stubby arrows, as is that one, but I can't see any restriction on where this one goes in box 7. It can go in all 3 places, I think. These two are having more effect in the rows than they're having in the columns. But there's no reason, again, I might be misspeaking here, but I can't see an immediate reason that's jumping out to me why these can't actually be blue. If they were blue, they would appear in, one of the 3 possible positions in row 6. If they weren't blue, they would mirror into one of those 2 positions, which is also fine. Ooh, I'm not sure I like this, actually. I'm going to actually get rid of the colouring here and start again. It's not an auspicious start, but this is what happens when you try and live solve puzzles, is sometimes you go down rabbit holes that lead to nothing. Okay, so let's come back to these 4 digits. Is there something about these 4 digits that has to be... Oh, right, yeah, now that's a thought. That's a thought. We've got lots of 3-digit or 3-digit arrows. Oh, yes. Now, hang on a moment. Hang on a moment. I think I've missed a trick here. Let's look at this side of the grid first. There has to be... this is... Yeah, okay, I've got it. Right. Here we go. Here we go with something sensible at last. There has to be a repeated digit between these squares here and these squares here. How do we know this? Well, let's imagine there wasn't. Let's imagine that purple, whatever's in those purple string, none of those digits appear in the blue string. What would the implication of that be? Well, this would be the minimum we could make the purple digits and the blue digits be then would be a 1, a 2, a 3, a 4, a 5 and a 6. That's the triangular number for 6, which is 21. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. And that would be the total for those 2 cells. Well, there is simply no way you can make those squares add up to 21. The maximum you could put in there would be an 8 and a 9, which add up to 17. So we know that there is at least one repeated digit between purple and blue. But how could there be more than one repeated digit? I don't think there can be, because if there's more than one repeated digit in these strings, where are you going to put that digit in this triple here? And this is where I think the short stubby arrows come into their own, because let's imagine there's a 1 and a 2 here, and a 1 and a 2 here. Now I'm faced with the task of putting 1 and 2 into these three squares, and you can see it's impossible. I can put one of them here, but the other one will go into one of those squares, and whichever one it goes into, it will get transposed into a box that contains itself. So these two squares become very problematic. So what that means is that there is exactly one shared digit between purple and blue, and that digit goes there. So this is the common digit between purple and blue. Now, is that digit limited in size is the next question. I presume it can be little. That's not going to put very much pressure on these two squares. So the question is, how high can it be? So if this was a 4, let's try 4. So now what I'm saying is that there's a repeated 4 in those squares. So the other digits can be 1, 2, 3, and 5. 1, 2, 3, and 5 add to 11. And double 4 is 8. So that gives us 19, which is impossible. We need to get down to 17 as a maximum. So 4 is not possible in this square. What about 3? 3 is probably not possible either. Then you'd have the minimum you could have in the rest of it would be not double 1. You've got double 3, 1, 2, 4, and 5. 1, 2, 4, and 5 is 12. Double 3 takes us to 18. That's impossible. You can't use 3, because then you'd have to have double 9 in those squares, and you can't do that because you'll break the rules of Sudoku. So this square is 1 or 2 now, and let's check what that does. So if we've got 2 here, you've got a 2 here, a 2 here, and the other digits can be 1, 3, 4, and 5. So 1, 3, 4, and 5 is 13. Double 2 is 17. So that does get us to an 8, 9 pair. So, okay, what does double 1 do then? That's going to be the question. So we get double 1, 2, 3, 4, 5. 2, 3, 4, and 5 add to 14. Double 1 takes us to 16. Which couldn't be double 8. Okay. So these two digits here are definitely either a 7, 9 pair or an 8, 9 pair. So there is a 9 in them and there is no 6. That is so clever. There is definitely a 9 in one of those two squares. And there is no 6. It's either 7, 9 or 8, 9. And the same must be true. Yes, the same is exactly true. This is what I should have picked up immediately, is look, there is a massive symmetry going on between this arrangement of circles and these short stubby arrows. In each case, you get two stubby arrows in the column which transpose themselves back into the boxes and therefore limit what's possible in terms of repeated digits. So again, just do the same logic on this side. This square must be a 1 or a 2. We've now got a 1, 2 pair in row 5. And aha, now what about this? This arrow here now can't have a 1 or a 2 on it. So the absolute minimum value of these two squares would be 3 plus 4. The minimum value of this would be 1. So 3 plus 4 plus 1 is 8. This square definitely has to be at least equal to 8. 3 plus 4 is a minimum. So this square has to be a 1 or a 2. And this arrow has to have a 3 in one of those two positions. Because if it doesn't have 3, the minimum this domino could be would be a 4, 5 pair. And that's already 9 before you take into account this digit. Okay. And now, oh yes, the other thing I've got to keep track of is that there's definitely a 9 in one of those squares. So we have an X swing on 9s. What do I mean by an X-wing on 9s? Well, we know that there's a 9 in one of those two squares in column 2 and a 9 in one of these two squares in column 8. So that means, what's the implication of that? Well, the implication of that is for the rows. And the way to understand the implications of X-wings is to ask simple questions like, in a correct solution to this puzzle, how many 9s are you expecting there to be in row 1? The answer is 1. There's going to be 1 9. How many 9s are there going to be in row 9? 1. There's going to be exactly 1 9 here and exactly 1 9 here. So there are 2 9s altogether in those 18 cells of the grid. But we've just said that there are 2 9s in those 4 squares as well. So what we cannot do is put any more 9s into row 1 or row 9. If we were to try and make this square a 9, now there are at least 3 9s in 2 rows of the puzzle, and that's too many. So we can rule 9 out. Well, we could never have put 9 on the arrow here, or these arrows. 9 can't go in here, or here, or here, or here, or here, or here, and it can't go on arrows. So is that a meaningful restriction? Maybe not, actually. So these 2 circles here now, we know they can't be 9, and they have to be, if this was a 1-2 pair, they'd be at least 3. But that means they've got a lot of degrees of freedom, which is disappointing. Oh no. What about, where does 9 go in box 7? Because we can't put 9, we know 9 is not in these 2 squares because there's a 9 in one of those 2 circles, so we also can't have 9s in these strings of cells. You can never put 9 on an arrow. You can't put 9 here, because if you put 9 on the short stubby arrow, its reflection is this square, and that removes our ability to put 9 into one of those 2 cells, where we know that there must be a 9. So 9 in box 7 is a bit restricted. It can't go one of 3 places, I think. Is the same true? Yes, it's the same logic actually. The 9 is the same up here in box 1. What about 9s in box 3 then? Same logic again. Okay, yeah, there's some symmetry around the positions of 9s. I bet the 9s down here are going to be restricted to those 3 squares. Let's check. 9s can't go there, can't go on an arrow, because this obviously would then have to be 10 or higher. Can't go here, it would reflect. Yeah, it's the same. Okay, well that gives us a little bit of a deduction. Where does 9 go in row 7? Not those 3, not those 3. So there's a 9 in one of these 3 cells. Same is true in row 3. So there's definitely a weird symmetry about this puzzle. Okay. I'm not sure this colouring is helping me very much either, so I'm going to get rid of that. Let's try and work out what to do. I'm tempted to think this must be something set related. Maybe on this row and this row. I'm just going to have a quick look at something. If I do those 2 rows, oh, this is not going to work actually, is it? I'm not going to delete enough digits. So orange is 2 sets of the digits 1 to 9. Blue is 2 sets of the digits 1 to 9. Anything that appears in both sets. Oh no, this is horrible. This is just not absolute nonsense. Sorry, that's not what we should be doing. What I want to do, I'm just not sure I can quite see the set that's going to do it, is I want to somehow put these 3 digits in one set this digit in a different set, and then I can cancel them from both sets. And if there's some way I can do that using all of the long arrows, I'm going to get quite a lot of interaction between the sets. The problem is they keep missing each other, don't they? These 3 digits and these 3 digits don't see those 3 digits at all, and they don't see the circles either. I don't think I'm quite visualizing how this restriction works. I mean, maybe we should just try and do really simple stuff, like that's clearly a set of the digits 1 to 9, that's clearly a set of the digits 1 to 9, and then these 3 squares add up to this one. So if I remove those 3 squares, or these 3 digits from the orange set, and then remove this digit from the blue set, I now know that the orange digits and the blue digits still sum up to the same total. I could remove this from orange, this from blue. But this is the problem with, I think, this approach, is that unfortunately, because this arrow doesn't live in orange or blue, there's very little I can do. I mean, I can do stuff to start doing stuff like this, which is, so now there is still a relationship between blue and orange. I could delete that and put that into blue. Just wondering if I can get a big restriction by putting loads of things into the same column, but I don't think this is doing anything. I've now got 15. Oh, this is nonsense, is it? I've still got a 5 string here. Well, So hang on, let me just think about this. I'm still in a position here, I think, where it's true to say that orange and blue add to the same total. But orange has a maximum value. If I put high digits in orange, I could make those 5 digits as high as 35. And if I put low digits in blue, this could be a minimum of 15, and they could be 1 plus 2 plus 3 plus 4, so that would be 10, 25. So there's still quite a lot of degrees of freedom. Just need to check my phone. What was that about? That's fine. So this is not correct, I don't think. Don't like it. Don't like it. Sorry. Need to somehow get. I want this and this to be in the same set. So do I have to do boxes? Is that what I've got to do? Let's try boxes instead of rows and columns. So if we put those in the same, so that's 2 sets of the digits 1 to 9. Now what's a useful thing to so now I need to get these 2 in a different set. Let's do column 2. So maybe we just stop there for a moment. So at the moment, it's true to say, in fact, let me just do some cancelling down and see if I can see what it is true to say. Then I've got these 2 are in the same, they are also sort of coloured the same. Those 2 are in different colours. These 2 are in different colours. Oh, that can't be right. Oh, this actually might be interesting. If it is interesting, I will definitely go back and explain what I'm doing here. I've got 1 digit left in there, but then I only put 1 blue set in. This definitely feels... I could cancel those down as well and replace them with those. Now I've got a situation where this digit plus 45... Yeah, this is definitely, well, it's definitely restricted enough that I want to look at this more. So let me just unwind a little bit and talk about what I'm doing here. So, first thing I did was to highlight 2 complete boxes of the Sudoku. Now, these orange squares, if we correctly complete the puzzle, will be the digits 1 to 9 once each. These orange squares will again be the digits 1 to 9 once each. So at this point, the digits I've highlighted are 2 complete sets of the digits 1 to 9. Now, I then highlighted this in a different colour. This column is 1 set of the digits 1 to 9, because in a correctly completed puzzle, that's what will appear in column 2. So at the moment, the difference between the blue set and the orange set is 1 complete set of the digits 1 to 9. Now, if I was to remove whatever digit appears in this cell, let's imagine this digit was a 2 in the correct puzzle. If I was to remove this 2 from orange and blue, it would still be true to say that the difference between orange and blue is 1 complete set of the digits 1 to 9, because this digit appears in both blue and orange. So if I remove it from both sets, I'm not affecting the difference between those 2 sets at all. And the same is true obviously for any cell that has both orange colouring and blue colouring. So we can remove these 3 cells, we can remove these 3 squares, and at this point it is still true to say that the difference between the orange cells and the blue cells is 1 set of the digits 1 to 9. So if this was a 1, 2, 3 triple, we'd find, let's just make sure everyone's on the same page. Let's imagine those, that's not going to work with the arrow, so let's not do that. Let's make those a 1, 2, 3 triple, which I know won't work with this arrow, but I just want to make the point. You've now got a 1, 2, 3 here, a 1, 2, 3 here. We would know at this point that the orange cells were a complete set of the digits 1 to 9, because that was the difference between the blue and the orange set. So we've got the same digits here, so the remaining 9 digits have to be 1 set of the digits 1 to 9. We don't know the ordering, but we know that they are a 1 set of the digits 1 to 9. Now, here there are a few interesting things we can note. The first is that these 2 cells, whatever's in there, appears in orange. So I can remove that from blue and from orange. This short stubby arrow is the same. This is in blue, this is in orange. I'll remove it from both, therefore. And now it's starting to get really interesting, because I've actually only got 1 blue cell left. So let's remind ourselves of where we are up to. This blue cell appears somewhere in orange. We don't know where, but it does. And the remaining orange digits will be 1 complete set of the digits 1 to 9. Now, what I think is, if I remove these 3 squares from orange, you can see that the sum of those 3 digits is the same as this arrow. So I can remove those and replace them by making that orange. I can remove these and replace them and make that orange. And I can't now say that the sets of the digits are the same, but I can say that the mathematics of what we described is the same. In other words, blue, whatever blue is, plus 45, which is the sum of the digits 1 to 9, is equal to the sum of all of these digits. And that feels to me, at least, like it's going to be quite difficult, because this is at least 46. So if I make this a 1, these orange squares have to add up to 46 exactly. And the maximum I could make them add up to, if this was 789 and this was 789, you'd get 48. So there's hardly any freedom here. And I'm not even sure it's possible that this... Can you actually do 789, 789? Because aren't you going to get a problem with these again? Oh, this is ridiculously clever if that's the case. It is, isn't it? I think it is. If these were the same digits, you would definitely have to have, yeah, one of the digits in this domino. Let's imagine these were all the same. I think that's probably best is to do an example like this. Now I think it's true to say that one of the digits in this domino is one of the digits in that domino. And that we can prove that to ourselves just by doing this. You can see one of the digits down here has to appear not in this square. And now you've got a problem. We've broken the puzzle. Because now I've got to find a place for 7 in one of those two squares, and it can go in neither because it will get reflected by short stubby arrow logic back into a box that already contains itself. So that's absolutely, well, it's amazing. Because what that means is that we can't, it's reduced a degree of freedom, hasn't it? Because if I can't make these 789, 789, then the best I can do is 789, 689. And I'm closing the gap on this digit here. I'm actually also wondering whether how many repeated digits are there between this orange set and this orange set? That's an interesting question. Is it possible there is only one repeated digit? Oh no, well, we know 9 is repeated. Actually, hang on, Simon. Come on, use your brain. There's definitely a 9 repeated because I know there's a 9 in orange there and I know there's a 9 in orange there. So does there have to be a second repeated digit or not? Because we know there can't be a third repeated digit. We've proved that. So if you've got one repeated digit, you'd have double 9. Let's actually put some numbers in so it's a bit more visually obvious. And then 8, 7, 6, 6, 5, something like that. That would be the maximum. If there's only one repeated digit, that's the maximum we could make these digits add up to. So we'd have 18 here, plus 15 is 33, plus 11 is 44. 44 is not the same as 46 or 47. So that's not possible. Oh, this is so clever. So there are 2 repeated digits exactly between in this little triomino here and this triomino here. We know one of those digits is a 9. If the other digit is an 8, then we've got 9, we've got double 9 and double 8, so that's 34, plus 7 plus 6 is 47. Ah, bother. 47. So it could be 7 plus 6 or 7 plus 5. All right, let's try and rule out. Let's try and rule out a repeated 7 then. So if we've got double 9 and double 7, then you've got 32. Plus 8 is 40. Plus 6 is 46. Oh, that works as well. Oh, bother. Bother. So actually, what have we learnt here? We have learnt that these digits contain definitely double 9, either double 8 or double 7, but actually both of those is possible. If it's double 7, it has to be 8 and 6 that go with it. Oopsie, hang on, let me just read that. Okay, I don't know what that is. If it's sorry, if it's double 7, it's 8 and 6 that go with it. If it's double 8, oh, then we could have a 5. We could have 7 plus 5 and get to 46. So these digits are either 5, 6, 7. Oh, whoopsie. 5, 6, 7, 8, or 9. That's a bit depressing, actually, isn't it? That seems to be as far as we can take that logic, and it's not nearly as good a restriction as I was hoping for. I don't even know what this is. I don't even know what the second repeated digit is. Bother. Bother. Right, okay, but presumably I can do the same exact thing over here, can't I? Because of the symmetry. Let me just double check. So let's use a different colour this time. I'll use red. Yeah, red's lovely. I can see the arrows against a red background. So that's 2 sets of the digits 1 to 9. Let's use yellow. Cancel out the common digits. Cancel out the common digits there. Transfer these down to here. And we get, yeah, we've got the identical issue. We've got the absolutely identical issue. So again, we're going to have to, all of the logic we've just done on the left-hand side must apply on the right-hand side as well. Which means these squares also are therefore 5, 6, 7, 8, and 9. And again, we've definitely got repeated 9s. We've either got repeated 8s or repeated 7s as well. Yeah, the other thing actually I've just noticed is that if you do have, say, repeated 8s, what you can't do is have the repeated 8s in those positions, because that will put an 8 in one of those positions. So the repeated digits are always in this pair. So we already know there's a 9 in one of these, but the other digit is going to be the repeated digit as well, which is a bit interesting. Oh, that square. Oh, hang on a minute. That square, this square is interesting. I don't know, it keeps deleting the arrow tip when I click on it because it gets a bit paler. But look at this square where the cursor is. That can't be a 9 or an 8. No way. Because that's going to... In fact, it can't... Oh, this square is very interesting. Let's look at this square. It's on a 2-cell arrow that adds up to this digit. So if that's even as high as 7, we've got a problem. Because if that's a 7, what's this square? The answer is 8 or 9, and now I've got 4 cells in row 9 that have to be selected from just 3 different digits, so that's definitely not 7. So this is not 7, 8 or 9, it's 5 or 6, which means this square is either 6 or 7 or 8 or 9. If I could just get rid of 6, I'd have a 7, 8, 9 triple. Can that square be a 1? Maybe, depending on the value of this square. From my X-wing, I know there's no 9 in here, don't I? So this is 6, 7, or 8. I know that's not a 9 by X-wing logic. Remember, that was the fact that we had to have 2 9s in those 4 squares, which feels a very long time ago. I've also got definitely got a 5 or a 6 here. Yeah, this is right. Right. Hang on. These 6 digits together, we know have to add up to 46 or 47. But what we didn't have in any of the options we looked at, we never had a 5 and a 6 in those 6 squares, did we? We either had 99, 88, 7 and 5, 99, 88, 7 and 6, or 99, 7, 8 and 6. So this digit, being a 5 or a 6, means that you cannot have any more 5s and 6s in those squares. And that means I've got a 789 triple in box... Oh, yeah, look, I've got a 789 triple in box 3, and that's a 7, 8 or a 9. So I've now got a 789 triple in row 1, which means that square is not 7, 8 or 9. Now I've got a 5 or a 6 in orange, which means the same logic can be applied to the rest of orange. You can't repeat 5 or 6 in any of those cells. So now I've got a 7, 8, 9 triple. Oh, this is it. Oh my, this is just ridiculously clever. Look, I've now got a 7, 8, 9 triple in row 9. That square has to be a 6. And if that square has to be a 6, that square has to be a 5, and that square has to be a 1. And I think that's it. I think we've got digits. It's taken me 41 minutes, but I think we have digits. Let us just backtrack for a moment, though, and admire the absolutely incredible logic that Emmettcito has built into this puzzle, because it is incredible. So, the magic here is that this square, because of this arrow, this has to be a 5 or a 6, which means there's no more 5s and 6s in any of these cells here. That created a 7, 8, 9 triple here, which combined with this square makes this square a 5 or a 6, which makes that the low digit in this 6 sextuplet. So we can't have any more 5s and 6s over here, which makes this a 7, 8, 9 triple, which combines with its friend here to force this square to be a maximum of 6, and it can't be any lower than 6 because this has to be at least 5. That is, I mean, correct me if I'm wrong. Please correct me if I'm wrong, but that is staggeringly beautiful Sudoku setting. That is, I mean, it's ridiculous. It's ridiculously clever. And hopefully it will be a breakthrough that takes us forward in terms of solving, because now if this is a 2, surely this is troubling. Yes. What's the minimum those two digits are? They've a 3, 4 pair is a minimum, and now we've already got to 9, so there can't be anything else, or we're going to have a problem. Now we know there's a 9 in that triomino there because of the logic we did earlier. Well, that 9 must therefore be there. That completes our x-wing. It gives us a 9 up here, where we knew there had to be a 9, because there was always a 9 in 2 of those 4 cells. So we've now got a 7, 8 pair here. We've got to have a 9 in this triomino. It's now got to be there. This is a 7 or an 8, so it must have a 1 on its arrow. The 1 is not there by Sudoku. I've got a 7, 8 pair in row 9. This square is definitely not a 9. So I've got a 7, 8 pair in column 3. I've got to put a 9 in this triomino. It's got to go here. That's no longer a 7, 8 or a 9. That means there must be a 1 on this arrow. It's either 1, 2, 4, 1, 3, 4 or 1, 2, 5. Okay. I've got a 7, 8, 9. So this arrow here. Ooh, yes. This square here can't be a 1 or a 2 by Sudoku. So this is at least a 3. So that could be a 1. This is at least a 4. But it can't be higher than 6. So this is 4, 5 or 6. This square here is 3, 4 or 5. And this is a 1 or a 2. This can't be 3 anymore because 3 plus 4 is 7, which this can't be. So it's not quite a triple though, is it? So I was hoping we might get a bit further there, but perhaps not. So can we... I'm not sure what to do here. I can put a 2, 3, 4 triple into the bottom row, just because I've got the other digits as sort of a sextuplet. Don't think that disambiguates this 7, 8 arrow. Oh, this 9 arrow can't have a 5 on it, look. So it's either 2, 3, 4 or 1, 2, 6, so that has a 2 on it. Oh, I suppose I can do the same trick with this triple here. This can't have a 5 on it. So if it's an 8 arrow, it can't be 1, 2, 5. So it's either 1, 3, 4 or 1, 2, 4. So it's always got a 4 on it, this arrow. Okay. Bother. So maybe I've got to use the short stubby arrows then. Is this where they're going to come into their own? So whatever's in there is in there. And it's not 9, because this one can't be a 9. So this is either a 5, or it's in that digit. Oh, lovely. Yes, 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 yes. Look, what are these two squares? Now by Sudoku, whatever is in these two squares has to appear in one of those 3 squares. Well, we can immediately get rid of this square is not green, because green already sees a 9. Now, what if this square was green? If this square was green, that square would be green, and these two greens would see each other. So this square is not green. So green is in fact 5, which is just a write-in. We can just do both of those digits. I'm not sure that this isn't going to just keep giving this sort of logic as well, because what about those 2 digits? Well, those 2 digits are now not 5, so they must be a 7 or an 8. So those 2 digits are either double 7 or double 8. I've now got a 7, 8 pair here. I've got a 7, 8 pair here. And maybe I can do the same on this side of the grid. So where is the useful way of thinking about this? That's the question. I was just seeing if there was an easy win. I'm not sure there's an easy win. These 2 cells, whatever they are, they'll not be there, because that was going to repeat purple. They're not 9, so this is a 5 or a 6 into these squares. That might be helpful, but I'm not sure it's quite good enough. Those 2 squares have to be a 7, 8 pair, exactly the same logic as on the other side. So we've now got 7, 8 pairs here. Those 2 squares have to go on this arrow, which is probably interesting. I just can't quite see why. Right, come on, Simon. I feel like we're close to a breakthrough now, even though we haven't quite got it yet. That square there is purple. Sorry, brief interruption. Voldemort-related argument. These things happen. I think it's sorted out. Let's hope so. So what had I just done there? I'd highlighted a purple... so I'd been looking at those, had I, and seen that those transpose into this square. We've got the same on the other side, of course. These 2 transposing into that square. So actually we can remove the red from that square. In fact, maybe that's not a bad idea. Do we want to keep all of the highlighting that we've got? Maybe not. Let's get rid of some of this. Tidy up the... Why is that? Oh, that's orange because It was part of the original orange triominoes, wasn't it? Do we need to keep this behind? Probably not. I'm actually going to get rid of loads of colouring. There we go. So, and take another stare at the grid. We've still got 2 short stubby arrows left to, oh no, 3 short stubby arrows left to use. Let us use those. We can, oh, well that can't be a 9 because that's going to put a 9 on this position and that's going to break. So let's get rid of a 9 from here. This square sees, what does it? Well, between the 2 of them actually, I can see 1 and 2 are both, because this can't be 1 or 2. So we can't be 1 or 2. 3 might be possible. 4 might be possible. 5 isn't possible. 6 isn't possible. 7 and 8 look odd. I'm going to think about those in a minute. And 9 is impossible. 7 or 8. Does that just mean it would be different from these 2? So maybe that's still possible that they can be 7 or 8. I'm not sure. Bobbins. Right, okay, what about that one? Oh. This one actually sees a 1, 2, 3, 4, 5. Well, it sees 1, 2, 3, 4, 9, and then 5 in the box. So, oh, good grief. Right, so this row actually is oh, yeah, okay. Right. Take a step back and look at this row, Simon. I think I could have done this the moment I got 5s up here. Because of this 7-8 pair, look. That square's a naked single, isn't it? It's got to be selected, from the row logic, it's got to be selected from 5, 6, 7 and 8. Now it's definitely not 5, and it's not 7 or 8. That is a 6. So the rest of this row now is either 5, 7 or 8. Oh, I wondered if we were going to be able to do the same thing in this column, but it doesn't seem to work quite the same way. We've not got as much 7-8 real estate in column 1 as we've got in column 9. That square can't be 5. Oh, now I've got a 7-8 pair in box 6, so that square loses its ability to be 7 or 8. That's because this becomes either double 3 or double 4. This square must transpose itself in here. So these are now... I think we might have to colour the 7s and the 8s. There seems to be a lot going on between 7s and 8s all of a sudden. This square now sees a 7-8 pair, which it did that before anyway. What should we do? Should we do this arrow or should we do 7s and 8s? I think I'm just going to do 7s and 8s just for a moment. Let me just have a quick look at them. This is red, so that's the same. This is different, so that can be orange. That's orange, therefore. This must therefore be red and transposes down there. So now, oh, yeah, okay, so where does red go in the middle box of the grid? It's got to go in that square, so that square's not 5. So this is red. Now I've got a red-orange pair in the central row, which means this square is 5. Oh, this is gorgeous now. Look, that's a 6, that's a 6, and that's a 6 at the top of the grid. That's 6. Sorry, I'm just trying to see whether this is doing an awful lot of things all of a sudden. That becomes a purple 6. That's a 6 now, because you can't put 6 on a 7-8 arrow. That puts a 6 on this arrow, which is a 1, 2, 6 arrow, therefore. And that's not a 6 on it. But more than that, this 6 is doing something to this arrow as well. So this is now 4 or 5. So this can't be 5 anymore. I've now got a 3-4 pair here. I've got this square's got to be a 3 or a 4 just to complete column 7. So we might end up having to colour the 3s and 4s as well. Oh, look, that's a 3-4 pair as well. Yeah, oh, this is nice. So now I've got 3, 4 here, 3, 4 here. So this arrow has to have a 3 on it. And if it has to have a 3 on it and a 4 on it, it can't be a 7 arrow. So that's an 8. And that fixes my colourings for 7s and 8s maybe. Yeah, this is now an 8. So this arrow might be forced, I'm not sure. This 8 is seeing this square, which gives me a 7 here. This is a 1, 3, 4 arrow. Let's put that in and see if, well, that tells us this digit is a 2, just to complete this box. And if that's a 2, that tells us that's a 1, that's a 2. There's now 2 forced onto the 8 arrow here. So this is 1, 2, 5. This is a 3, 4 pair. This is a 3 or a 4. There's a 3, 4 pair in row 4. I need 1s and something, 1s and 5s into these squares, which is presumably, yeah, it forces the 9 arrow to be 2, 3, 4. This is a bit terrifying as well, in case I suddenly come up against a contradiction. 8 can only go in one position. That's got to be a 1. 8 gets its colour of orange. This square's a 3 or a 4. Hopefully something will disambiguate these 3 4s at some stage. Oh, look, I've got a 3, 4 pair in that row, so that square's got to be a 1. Another 3, 4 pair emerges from that. This square's a 1, this square's a 5. Those 2 squares are an 8, 9 pair of all things. Don't know if we can figure out the order. Let's colour in the rest of our 8s. Have we got any more 7s to colour in, maybe? 9s? 9s didn't get a colour. Sorry, colourless 9s. This 8 is doing the 8 and the 7 down here as well. So that's more colouring we're able to do. Although I'm not sure how useful that colouring is. It puts a 7 in one of those squares. Those 2 squares are now a 2 and a 9, which... No, this 2 is useful. That 2 deserves to be blue, especially as it's resolved those 2 cells for me. So this 9 might be helpful. Yeah, that's a little bit helpful in terms of column 6. Where does the 9 go now? It can't be here or here or here. So it's exactly there. And now this column's suddenly become interesting. It needs a 5. And where does the 6 go? In column 6, only in that cell. So that's 6, that's 5. That's not 6, which means this is 6. Get rid of the 2 pencil mark. And pray that this is now solved. Is it solved? I'm not sure. I'm actually not sure. I feel it's going to be something to do with this top row. Yes, it is. Of course it is. I've got a 1, 2 pair, which means this is a 5. And that 5 is huge because it's going to disambiguate the arrow. Forces this to be 4, 3, 1, 2, 1, 1, 2. That 3 has given me a 4 there, which gives me a 3. Is that going to go through the grid? I think it is. What an extraordinary puzzle this is. I mean... Yet again, we're faced with one of these situations where this is just one of the greatest Sudoku puzzles you could ever wish to solve. And I just wish I knew what to call a video like this, that it becomes, you know, essential viewing for fans of Sudoku. Because it really, this is just wonderful. 9 and 8 go in, 8 and 2 go in. That 4 is removing a 4 from this square. So these are from 2, 3 and 7. Don't know if we can do that. Oh, we need to put a 1 into this box. So that's going to be 1. That's going to be 5. That's a 5. That's a 7. That fixes the 7. Forces the 4, forces the 4 and the 3. This column needs a 3 in it. Whoa, 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 whoa. Don't get too quick, Simon. It won't help you to solve the puzzle. 2 goes here, 3 goes here, 4 goes here. And we have solved the puzzle. Oh, wow. Just wow. What an extraordinary idea. I still don't know why it's called Bowser's Castle, by the way. If anybody understands that, I would be interested. I think there's probably some sort of Super Mario knowledge required, which I don't have. Which I should really have, but I don't think I do. Have I coloured in everything that deserves colouring? 1s, 2s, 3s, 4s and 9s remained oh, 2s need colouring, don't they? There you go. So 1s, 3s, 4s and 9s are the only things uncoloured. Oh, 1s I suppose deserve to all be yellow, if we're really being consistent. There we go. It's where to start with this. The logic around these arrows is really, really precise and interesting, and the fact that it sort of forced this 1-2 pair, I thought that was going to be the break-in, but it wasn't at all. We actually had to figure out this weird relationship between, it was something like those cells and this cell that had a relationship that was far from obvious. But the effect of that was utterly gorgeous. The fact that you got these 5, 6, 7, 8, 9 arrangements around the grid. Can't actually remember exactly how they were disposed, but then we got this from this arrow. This arrow just did wonders. It forced this to be a low digit, which then forced the rest of it to be a high, and then we got that effect going round boxes 1, 3, 7 and 9. It was I'm just lost in admiration for things like this. I really am. I really hope some of you tried it. I really hope some of you saw the beauty of this puzzle, because it deserves so much credit. Wow. Wow, 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 wow. Loved it. Thank you so much for watching. It's another long video, but I hope this puzzle, you'll agree with me, it definitely deserved it. And we'll be back later with another edition of Cracking the Cryptic.